Hello. So Simon got a PhD in mining engineering from Sustainable Mineral Institute at University of Queensland. He worked for 18 years in Australian mining industry in research and development. Then he headed to Europe for 3 years at University of Liège in Belgium, researching circular economy and industrial recycling. Now, Simon is an associate professor of geometallurgy at GTK, Geological Survey of Finland, in Circular Economy Solutions Unit. So thank you so much for joining us. Simon, over to you.
So I'm going to talk to you today about a research project that I'm part of. This is the reprocessing graphite tailings at a Finnish deposit. I'm part of a team. I'm not doing most of the work, so I'm not the first author. So this is about the Aitolampi graphite deposit in Finland. It has not actually been mined yet, so we're just operating off drill core and trench cuts. This deposit has graphite grades of anywhere between 4 and 12%, so it's pretty good grade. But it also has a sulfide mineral content anywhere between 3 and 9%. So we've identified 5 ore types, highly variable texture. So we've got an acid mine drainage problem here. We can get the graphite out just fine. There was a geometallurgy study to show that. But now this is about what do we do with the tailings. We've got a new scanning micro XRF unit, which is proving to be very, very interesting. And it can actually, those images you see on the right are drill core, and the biggest one was 20 centimeters long, and it was able to XRF map that drill core down to a resolution of 20 microns. So we've got mesotexture. It's great. Anyway, so this was the ore to start with. So what we have is a pilot run that was done at SGS, and they've given us their samples as tailings. So we've got their tailings samples after the graphite's been taken out. The plan was this, where we take the sample and we're going to, as we receive the sample, we're going to characterize it, chemical assays, 4-acid digests. It's actually Lichio S and Lichio C, not Ultra S and Ultra C, different test. And acid mine drainage assessment. Then we're going to process the sample and see if we can actually do something with it. So if we characterize the base level, then we're going to look at magnetic separation, gravity separation, and acid leaching, and then combinations thereof. And I can show you some of the data today. It's still in progress. So each sample will be characterized. We'll go into a chemical assay where we're going to, so the chemical assay is what's actually done on site routinely. And it's also the best way, it's the most reliable way to get sulfur and carbon. Characterizing graphite, as it turns out, is a real pain in the you know what. We're also looking at X-ray diffraction for bulk mineral analysis and XRF. And some of the samples will be put into automated mineralogy so we can see the actual texture of what we're dealing with. And some of the samples will go off to acid mine drainage, where we want to actually sort of measure and see exactly what we're dealing with. All tests, process tests, will be done in this context here, where we've got the feed going in and the products coming out, where they'll be characterized in a way that we can do a mineralogical mass balance, so we can work out what went where, what minerals report to what subproducts. So the XRD of the tailings, there were two samples from different ends of the deposit, east and west. So, so as you can see, we've got mostly quartz, feldspar, and plagioclase. We've got quite a lot of sulfides in there, which is, but the XRF is actually providing us the elemental map, and this is interesting. So, in terms of acid mine drainage, sulfur is a problem, and we're allowed to have 0.1% of sulfur, and as you can see, we're well past that. And in terms of parts per million, it's 1,000 parts per million. There's also a number of metals that are susceptible to acid mine drainage, and those are the thresholds. So every single one of those metals is past the threshold. Like zinc, we're allowed 200 parts per million, which is down here, but as you can see. And we've also got mercury in here that is, threshold is allowed to be 0.5 parts per million, but we've got 1.5 parts per million in the sample. So mercury is also a problem. So all of these things need to be addressed to actually have a clean tailings. So first we looked at magnetic separation. As it turns out, this is not done. The magnetic separation is not considered first. Usually with tailings, they either leave it in the dam and hope for the best, or they'll consider a leaching option. It's not always the case where they'll consider magnetic and gravity first, then leaching. So we're looking at leaching now. So the idea was to take the sample, it's been characterized, feed it through the unit first at a low intensity magnetic separation, the equivalent of a ferrite equivalent, take the actual tailings out of that, run it through at a slightly higher level for medium intensity magnetic separation, and then take the tailings out of that and put it through at high intensity separation. And we'll look at the concentrates for all of that, and we can reconcile everything to the final tails. So here's the data. And so nickel and copper. So the low intensity magnetic separation fell into 7.4% of the actual mass. And we've managed to get below the threshold for some minerals, but when you actually sum everything up together, like the tailings that actually come out into the tails, we're still not quite there yet. So magnetic is helping, but it's not enough on its own. So the medium fraction, the medium intensity fraction, that represents 6% of the mass. So if we summed the low and medium together, it'll be about 13% of the mass. And so we're actually reasonably close to getting to the point where we're removing problem metals like nickel and copper, but we're still not quite there. We certainly don't have enough in terms of sulfur. Sulfur is still quite... sulfur is just, if we did complete magnetic separation in the tailings, we're just below the threshold. But that represents way too much mass because the high magnetic separation represented 20%, 7% of the mass, and that's just not practical. So what we're going to assemble all the options together and recommend a combination of things. So it might be gravity, then magnetic, and then leaching, or thereof. But each one will have a engineering logistics profile. So here's gravity separation. We went through a shaking table, and we've got the concentrate, the middlings, and the low mass tailings. And we will collect those fractions, and we will characterize each one. So here's the data. So the concentrate represents, we're still sort of, about 8% of mass. So, okay, yeah, anything more than 10%, it's not really practical anymore. So it helps. And again, we are removing some material, but it's not actually enough. So the middlings is 72%. So we are actually able to separate some of this out. So, but that's not practical in its own right. And tailings was 18.9%. So what we're sort of looking at here is what minerals are falling into those categories. Like, are the minerals reporting it to gravity the same minerals that are reporting to magnetic? There'll be an overlap, but if we did combine together, what we'll be looking at, that'll be the next step. So now what we're looking at is actually looking at the leaching the sample as received without taking anything out. And so we're looking at different methods, and we're looking at targeting pentlandite first, then pyrrhotite, and then pyrite. And in rough contests, like our pyrrhotite will probably come first, then sphalerite, then pentlandite, then chalcopyrite. And pyrite traditionally is, a troublesome mineral to get hold of. So the experimental series that we're planning, and it's actually in progress now, is the pH and redox potential is measured at multiple time frames, 5, 15, 30, 60 minutes, 120, and 240 minutes. And then we'll actually get like an analysis in the pregnant solution. The residue slurry is washed, dried, and then we'll get some XRD results on the results of that. So this is what we're planning. I don't have the data to show that. The idea is at the end, we will have data on the ground for magnetic, gravity, and leaching, and then we'll make a judgment call and we'll make the assembly of them all together to work out what can be done. It will be nice if gravity works because we don't need chemicals and the capex is quite low. Magnetic is okay, but it does require power draw. So they were relatively low. And if we can reduce the volume that has to go off to the leaching circuit, that would be very nice as well. Thank you.
Thanks very much, Simon. It's really great to get straight into looking at some of the data there, and I'm also looking forward to the discussion with you afterwards. So I think we now will move on straight away to our second speaker. Yeah, Rosie is a geologist and resource engineer, and her work focuses on sampling, geostatistical modelling, and geometallurgical characterization of tailings deposits to assess resource potential. She's currently doing her PhD as part of the Sultan European Training Network for Remediation and Reprocessing of Sulfidic Mineral Waste at the Helmholtz Institute Freiburg for Resource Technology in Germany. So with that, I will pass it over to you, Rosie, and looking forward to your talk.
Thank you. So hello, everyone. Good morning, good afternoon, or good evening, wherever you are in the world. Today, I'm going to be sharing some of my research from my PhD project, and specifically how we can assess the resource potential of tailings and focusing on sampling and modelling. So as you probably all know, the tailings are a global challenge at the moment because we're just producing more and more of them as our demand for raw materials grows. And it's a pretty unsustainable path at the moment. So what can we do about this? Well, one thing would be remining and reprocessing of tailings deposits. Often they contain residual contents of the metals which were previously recovered due to low processing efficiencies, or also critical raw materials that perhaps weren't of interest before. The other thing we can do is use the tailings or reprocessing residues from tailings in industrial applications such as ceramics or cements. But in any case, we need to assess the resource potential to know what is possible. I want to touch on this briefly. Tailings are often deposited as a slurry. And when this happens, there's a sedimentary style deposition of the tailings. So we have a sorting of the particles based on size and density away from the spill points. So as you can see in this figure here, we have coarser and denser particles being deposited nearer the dam walls, and then finer and less dense particles travel further into the dam. And this can create trends in the composition of the materials. And you can also see this very nicely in these photos at the bottom. We have these kind of beachy areas around the dam walls where the coarser material is deposited, and then finer material in the center. The case study that I've been working on during my PhD is the Davishach tailings deposit, and it's located just outside of the city of Freiburg in the east of Germany. It was operated between 1944 and 1964 and contains around 760,000 meters cubed of sulfidic flotation tailings. And these are from flotation of polymetallic hydrothermal vein ores to recover zinc, copper, and lead mainly. And the tailings still contain residual contents of these metals, as well as some indium and hazardous elements such as arsenic and cadmium. And as I was mentioning before, we have this sedimentary style deposition. And in the figure on the bottom right, you can quite nicely see a fan-shaped structure that resulted from this sedimentary style deposition. So we first performed a sampling campaign on the tailings. And this involved sampling the 1 to 3 meter layer, so just a shallow zone of the tailings. And we have these samples where the orange points are on the map, on a 30-meter grid, nested grids of 15 meters and 7.5 meters, with additional random and twin holes. And in total, this is 68 samples. Unfortunately, we couldn't sample this southern part of the tailings, because there's a lot of rubble and construction materials on the surface that we couldn't drill through. We then analysed all of these samples for geochemistry. So if we want to assess the resource potential, we need to make a model of what is there. So in this case, we decided to use geostatistical modelling. And we were interested in the zinc and lead and copper and indium, and also the arsenic and cadmium as the hazardous elements. As I've talked about, we have these strong underlying trends in the composition from the sedimentary style deposition. So we decided to use universal prigging. I'm not sure if everyone here will know what prigging does, but basically you have the limited data, so the samples we have in this case, and you can interpolate all the values across the spatial field using the spatial correlation between the data. And universal prigging is a specific type of this where you can use the trend in the data. So to do this, we had to fit these trends. And first we did this with the X and Y coordinates of the sample locations. So the kind of the correlation between the location and the composition. And we also did this with the grayscale values from a historical image. So the one on the bottom left of this figure, it was taken in 1967, so just after the deposition in the tailings ceased. And we found that if we extracted the grayscale values of the sample locations, it correlated very nicely with the composition. So we also decided to try and use this to fit the trend. The other good thing about using geostatistical modelling is that you can perform simulations, and this can produce equiprobable realizations. So multiple realizations of the reality that is actually the true distribution of what we have there compared to normal prigging or other interpolation methods. It just gives you one kind of smooth estimate. So for example, in the figure on the right, you can see the ground truth, which is our geochemical data, and then examples of 4 simulations of copper, zinc, and cadmium. And you can see that they're all slightly different, but they're very similar, and they show the same trend of metal enrichment through the center of the dam and depletion around the dam walls. And this is what we would expect from the sedimentary style deposition. The next thing we wanted to investigate was how to best sample tailings deposits for the robust estimation of grade and tonnages for resource estimation. We need to know that the estimates are good. And we also wanted to consider what uncertainties are acceptable for the grade and tonnage estimates for classifying resources and reserves. So we took these 16 different sampling schemes. A to F are all regular grids with a random point per grid square with a decreasing grid size. G, H, and I are the same number of points as B, but with different configurations. So we have a regular grid and then nested grids and then random points. And J, K, and L are the same as these ones, but with the same number of points as B. So in this way, we could test the sample density required for good estimates, as well as the best configuration of the samples. So how did we actually do that? Well, we took each of the 1,000 realizations that we had from the previous geostatistical modeling, and we overlaid these sampling schemes. So for instance, this figure on the right shows how we did it with scheme A. And we then sampled the ground truth, so the realization from the geostatistical modeling. And using these new samples, we performed the geostatistical modeling again. And you can see in the third column of the figure, we have the results from when we just used the X and Y coordinates to fit the trend. And on the far right, it's when we use the historical image as well to fit the trend. You can already see that there's a bit of a difference. So when we use the historical image, we better reproduce the spatial variability of the tailings. And if we want to think about this in terms of errors and uncertainties on the results, then we decided to look at the tonnages. So we estimated the tonnage corresponding to the original simulations, and then we estimated the tonnage after the resampling and modeling again, and compared these two results. And the figure on the far right shows as you increase the number of samples, so from scheme A to F, the error in the estimated tonnage significantly decreases. At a certain point, there's not much benefit of taking more samples. So maybe after scheme C, which I think is around 30 points or something like this, then probably it would not be necessary to take more samples. We can also see when we compare the black points to the white points that when we use the historical image, the error is typically decreased. So if we think about this in terms of classification of resources, perhaps for inferred resources, an error of plus minus 30% at an error of 90% confidence level would be sufficient, in which case sampling scheme A would already be fine. So only around 10 samples or something like this would be necessary. Whereas if we want a higher certainty, or a lower error for measured resources, then we would need many more samples. So we would need something like scheme C. And then looking at the configuration of the samples, well, we found that the regular sampling is best for producing robust tonnage estimates, whereas the random sampling better produces the spatial variability. So the regular grids tell us what we have, whereas the random sampling will tell us where we have it. And both of these will be important for properly assessing the resources and deciding how we would remine these deposits. So overall, it's probably best if we combine these two types of sampling. The other thing to note is that when we have exhaustive data, such as the historical image, it reduces the number of samples that are required and better reproduces the spatial variability. So perhaps also data like a geophysical survey might be able to help with this. It's not something I've investigated personally, but it would still be a similar type of exhaustive data. So to summarize, for assessing the resource potential of tailings, sampling is very important to begin with. So we need representative sampling across the whole area of the tailings to ensure that we capture this heterogeneity. So we know that we have this sedimentary style deposition, and we need to make sure we sample enough to really cover the trends. And we need a sufficient number of samples for robust grade and tonnage estimates. I've shown here that probably we don't really need that many once we've sampled it and have captured the different types of material. It can be quite homogeneous within these areas. And regular grids plus random samples are best for doing this, combining the spatial variability with the robust tonnage estimates. Geostatistical modeling is typically more accurate than simpler interpolation methods. And the added benefit of using something like universal kriging is that we can account for these trends in the composition and also produce multiple realizations rather than just one best fit. And this gives us a good idea of uncertainties, which is really important for going further along the mining value chain. Further steps that should be taken would be actually doing geometallurgical modeling, because we mine the minerals and not the metals. And other factors such as mineralogy, deportment, and particle size really influence the processing behavior. And we can integrate these into the models to really say what is recoverable and how we could optimize processing. I have started working on this, but I didn't have time to present it now. So yeah, thank you, and looking forward to your questions.
Very good, Rosie. So I think we are going to move now to our last speaker. So Alannah has over 40 years mineral exploration and open pit and underground mining experience across a broad range of metalliferous commodity in Africa and Australia. His recent roles include geology manager with Ectus Resources and Kingville operations in North Queensland, and exploration director with Muhutbu, managing grassroots biochemical exploration programs in the Tanami Desert. Previous senior geological position also includes chief geologist in Queensland with Kagara, geological superintendent at Eloy Mining for Barminco, chief geologist with SMC Resources at Hardley Castle Mine and chief geologist at Mount Launcher Gold Mines. So Jan, that's all yours now.
Thanks very much, Carol and Alannah, for inviting us along to this forum. It's a great pleasure to be able to present our activities. I'll just move on. Yeah, I work with EnviroGold. We're actively involved in trying to kick off some tailings retreatment opportunities around the planet. Our company logo there, Metals Without Mining, that's a fairly catchy phrase, but it pretty much sums up what we're trying to do. Because we're a publicly listed company on the Canadian Securities Exchange, I'm obliged to put up a number of disclaimers. You'll be pleased to hear I won't be going through that because it could take a little while. That's the first one, a whole load of corporate issues. And the second one, we'll be referring to some historical resource estimates at some stage, but a little bit later in the talk, for the Hellier deposit down in Tasmania. But again, we can probably gloss over that and let you guys catch up on that one at your leisure. Very quickly, I'll just run through our corporate background, where we've come from, have a look at our exploration methodology and our ranking methodology, cover off on a few challenges and solutions in the tailing business, look at a couple of projects that we're actively working on at the moment, and then wrap up with a few closing remarks. So our corporate background, EnviroGold Global is a pretty new company, grew out of a water purification exercise that was kicked off in the mid-2000s by our chairman, David Cam. He perfected some quite unusual water purification methodologies. And basically, I guess a couple of years ago, he asked himself, well, how can we develop this into a tailings treatment process exercise? So EnviroGold was kicked off a little bit over 2 years ago now to focus on, quite simply retreatment of tailings and environmental remediation. A little bit less than a year ago, we listed on the Canadian Securities Exchange as a public company, and we've got a number of really quite obvious objectives. We're very keen to reevaluate the viability of tailings around the planet, recover metals from those resources, remediate the tailing sites to improve the environment. We're very keen to prioritize stakeholder engagement in our efforts around the place. That's critical for us, getting a social license to operate. Obviously strive for zero harm. And I guess another one of basically our overall objective is to leave things better than we found them. So our exploration methodology is stunningly simple. Find the mine, you'll find the tailings dam. And obviously we've used imagery and Google Earth quite a lot to do that, in conjunction with essentially what's a large desktop review, which involves looking at a whole series of factors to try and essentially establish what is in that tailings dam or what might be in that tailings dam. So there's a lot of documentation you can work your way through, public reports, government records, a whole number of papers on metallurgical recoveries and so forth, and the geology. If you're lucky, there's a resource estimate available, but some of those are pretty flaky, and Rosie would probably be quite horrified at some of those because some of those are pretty flaky. In the absence of a resource estimate, we try and compile some sort of feel for what's in that tailings dam by looking at production records and recoveries. But obviously a lot of this information is piecemeal, and sometimes you can't get very far. Having said that, our exploration method is extremely low risk. We really don't spend a lot of money on the exercise. It's a low budget affair, but we can identify resources way cheaper than a standard exploration company does. We don't do any drilling. It's all really a desktop exercise. We've restricted our activities to a number of preferred jurisdictions where sovereign risk is deemed to be much lower. So they're really focused on Australasia and the North America, although we're starting to look at Central America, Europe and Africa. And again, we restrict ourselves in terms of what we're looking at, primarily precious metals, gold and silver. But I suppose as time goes on, we're starting to look more and more at PGMs and also some of the new economy metals and battery metals, nickel, copper and cobalt. Our ranking methodology, again, this is really quite simple. It's really just a 3 traffic light scheme: green, orange and red, green, amber and red if you like. And very early on in the piece, we ranked the project based on 5 groups of factors. I suppose there's the primary factors, which are really how big is this resource potentially, grades, tonnages, and also how much confidence do you have in that resource. A series of technical factors, which are essentially metallurgical. How difficult do we perceive getting the metals out of these tailings is going to be? A series of economic factors, which is essentially, are we going to make money out of this exercise, or does it look like we can make money? A whole host of operational factors, which include permitting, access, weather, how, just from a practical point of view, how difficult is this exercise? And then for us, a critical set of factors at the back end here, which is an ESG focus. Can we get a social license to do this? How amenable is the local community? And also with a view to the end of the exercise, just how complex is the closure of this site? I'm sure we're all aware of the issues with tailings. Most tailings are refractory. They're the most difficult part of the ore body to get out. Encapsulation is a serious problem, whether that's armored by something hard like quartz or other sulfides. Composite grains are always a problem in tailings, and the reason they end up in the tailings. We're particularly looking at what we call ionic gold and silver locked up in pyrite, arsenopyrite lattices, and there's quite a bit of that stuff around the planet. The traditional way of attacking those products has been to oxidize them. Things like the Albion process, they're very high energy demand, generally have to generate oxygen to do so forth, and emissions are an issue with those. Ultrafine grinding we're not keen on because that really relies on huge energy inputs. So we're trying to keep our costs down, and we've come up with a leach solution which we're particularly proud of. It's patented, so I can't tell you anything about it, I'm afraid, but we're looking at implementing that at a number of sites. And that seems to be particularly effective at what we call our sweet spot, which is polymetallic VMS deposits with locked up precious metals in those pyrite and arsenopyrite and other sulfides. So that's where we're focusing our effort at the moment. Current projects, we've got a couple on the go, really quite active at the moment. One up here, Buckens in Newfoundland, and the other one's Helier down in Tasmania. We've got a number of other projects we're looking at in North and Central America, and even having a little bit of a look in Africa, again, focusing on those lower sovereign risk areas. Helier is down in northwest Tasmania, right down the bottom end of Australia. That was a very large polymetallic VMS, which was mined for a period of 13 years, up to 2000. Produced about 14.6 million tons from underground, a big deposit, substantial deposit. A little bit of retreatment of tailings was done in 2006 to 2008 out of TSF1 here. Here's the mill down here. A couple of years ago, Helier Gold Mines commenced reprocessing on a very serious basis and have been operating ever since. Here's a recent resource estimate that they put out 18 months or so ago. There's still a substantial amount of tailings requiring retreatment. So the basic problem at Helier is that the gold is locked up in pyrite and arsenopyrite. It's not recoverable by cyanide leach. Hence, we've developed our leach process to try and attack this material. We signed a binding agreement with them earlier this year to get stuck into the tailings processing, and we're looking to construct a plant towards the end of this year to help retreat those tailings, and we're aiming to get 75% of the gold out and 90% of the silver. Helier is a fairly easy one for us because it's already permitted, it's already operational, it's an easy place to establish an operation. The next one's a wee bit different. This is Buckens in Canada. Mining finished in 1984. This was another large VMS deposit where they mined a similar quantity to Helier, 16 million tons, a fantastic deposit. Here's the township and the mine, the old open cut, and a couple of tailings dams. But for a period of 40 years, they tipped the tailings into the local creek. Here's the Buckens Brook running down here. And as you can see, there's a very substantial delta down in the lake. Not all of which is tailings, of course, but a lot of the tailings ended up in the lake. We estimate as much as 8 million tons. So to explore that delta, we've done, as a first pass, we did bathymetry on the flooded part of the lake. and also did a couple of ground penetrating radar surveys, which you can see here, which have picked up a unit that we call layer 2. Layer 1 is the water, layer 2 is the potential tailing zone. And you can see the variation in thickness, and the work has defined something of an arcuate structure through here off the front of the delta. It's at almost at where everything falls off the delta. And you can see that from that scale that we're getting up to as much as 4 meters thickness of a fairly soft, squidgy tailings unit. And we're in the process of vibrocore drilling that at the moment. It's not easy. There's gravel in there and all sorts of things which make the drilling difficult, but that process is currently underway, and we're optimistic we'll be able to come up with a resource quantity and a grade for this thing. So I suppose to sum up, there's no easy pickings in the tailings business. They're all difficult. That's as I said earlier, it's the refractory part of the ore body, the most difficult 10 to 20% to deal with. On the basis of the studies we've done, a huge proportion of the world's tailings are still essentially uneconomic. Even at current elevated metal prices, they're just not simply economic. We're looking at a number of very high tonnage, low grade exercises, but they require a high throughput rate to make money and a lot of capital expenditure. So for the moment, we're sort of focusing on our sweet spot, which is gold bearing polymetallic VMS tailings. And thank you very much.
Thanks so much, Ian. Ian, if you could just leave your final slide up, that'd be great, just so we don't have anyone rushing in on the YouTube screen. But yeah, thanks so much to all of our speakers, Simon, Rosie, Ian. That was such a great comparison of the different things that are required to mine these things, to mine these mine tailings, and the challenges involved. From metallurgical to sampling to just the practicalities of getting out there and what is the resource potential of these. So we've now got a little bit of time left for discussion.
I was really particularly interested in Rosie's study. So what is the residence time of what's this minerals like cadmium and zinc that you found in your study area? And did you also find a concentration of the material in the center? And did you find it also lowered down the actual deposition sequence?
Do you mean like how long it would take for the cadmium and zinc to be leached?
Yeah, exactly. Yeah.
Okay. Well, I think it depends a lot on the dynamics of water and oxygen circulation through the tailings. We did also have deep drill holes through the whole of the tailings, and the cadmium and zinc, well, actually all of the metals increase a bit with depth, but I think that's more in relation to the historical processing probably being a bit less efficient. So we don't see like a gradient due to any kind of oxidation or leaching processes of the sulfides. But I'm not really sure what the residence time would be. I think that most of these processes happen in the surface zone of the tailings, where there's more water coming in from rain, and then through the seasons this water rises and falls, and there can be more oxidation. So I think it's mainly focused in this kind of oxidation zone, which is like the first 1 or 2 maybe meters of the tailings, and further down I'm not really sure. I haven't really focused on these kinds of reactions. I was more focused on trying to assess the resources instead.
Okay, no, thank you. And then my second to last question, what is the minimum distance that you calculated to actually avoid sampling distance to avoid spatial autocorrelation?
So I don't think I really calculated that necessarily, but I mean I think the closest sampling I did with these resampling grids was maybe like 2 meters or so, or maybe it was a bit more than that, and that would already be too much for sure. So I think that anything above like 5 or 10 meters would probably be sufficient and would hopefully avoid avoid autocorrelation, but it really depends on the specific tailings deposit as well, and maybe also on different areas of the tailings deposit, because we have such strong trends in the composition. It might be very different. I'm not sure.
Thank you for that. And then my last question, were you using R to actually process some of your data?
Yes, I did everything in R. So I imported all of the data in, and like the spatial data for the historical image and the polygons for where I did the modeling. So I imported all of that into R, and then performed all the geostatistical modeling in R. Okay,
that's really fantastic. I mean, a bit of a silly question, but would you be open to sharing your your script or not?
Yeah, I could do. I suppose I would need to clean it up a bit. It's a bit of a mess.
Okay, yeah, that's really awesome.
Yeah.
Okay, thank you so much.
All with open packages on R, so yeah, for sure I can.
Okay, thank you so much.
And with that, I will have to leave.
Yeah, no worries. Thanks so much, Rosie, for hanging in there for a bit longer, and best of luck for your next talk at the conference. And thanks.
If anyone wants to send any more questions to me via email or LinkedIn or something, then you're very welcome.
Great, thanks, Rosie. Yeah, so maybe I will segue over to Ian and ask a couple of questions that kind of a similar line from what was just asked Rosie. This sampling methods. I mean, you see you're doing all the desktop studies, but how does that fit into like the methodology that Rosie's been looking at? How does that fit into what EnviroGold's been doing and the future potential?
Yeah, sure. I guess there's a popular perception out there that tailings are nice and homogeneous, but as Rosie's found, and if you think about it, obviously they're not. There's very dramatic gravity and settling issues in a typical TSF. The only way I believe to sensibly sample a TSF is to drill it, and some of that's quite difficult, particularly if it's a flooded TSF to reduce oxidation. So drilling is quite critical, and trying to work out what the optimum pattern is also quite hard. You don't want to overdo it, and you don't want to underdo it. I'm thinking of a particular example I've looked at recently, which is a 50 million ton tailings deposit, potentially quite uniform material, but they drilled 5 holes in that, and they were all around the edge, and I've got huge alarm bells ringing. So each hole represents about 10 million tons of material, and they called that a measured resource. So yeah, I guess we haven't really wrestled with what's the ideal pattern. I think notionally a well-distributed pattern with spacings of the order of 25 meters is what you need, and that's what we're trying to target at our drilling we're doing into the Buckens Delta at the moment. Is start off with a broad pattern, see what the overall variability and variation is, and then focus in on the thicker part. Obviously need to do more drilling where the material is thickest and where your tonnage resource is maximized.
Yeah, thanks, Ian. It's so interesting to hear this. I mean, you can see that every tailings pile has its own differences, but also, yeah, like you brought up, if you're only sampling around the edge, but Rosie's study clearly showed that the middle has potentially quite different distribution in terms of metals. And Simon, maybe I go over to you. Do you have any comments on the sampling? I know you said you had, like, in your deposit, you were looking at samples from like east to west. And there was some differences there. Do you have any comments on the sampling method?
Yeah, sampling is done very poorly, right? When you're talking about a geostatistical study, they talk in terms of, say, 50,000 assay measurements across multiple drill holes. But when you get to the metallurgy end of things, in the good old days, 30, 40 years ago, they would take 10 samples and take an average of those 10 samples and then build the whole operation on those 10 samples. And they thought that was okay, right? And so the whole point of geometallurgy is to bring the concept of many thousands of measurements spread across the deposit in a in a grid, a geospatial grid, and then actually sort of running some statistics on the outcome. So the industry is actually evolving, and tailings is worse again traditionally. So once it goes into the tailing dams, it's just no one wants to know, traditionally, because and anything that is to work with those tailings will be seen as a cost for no actual benefit. So that is also changing. The industry is slowly getting used to the idea that actually it might be valuable, or it is actually sensible to actually treat those tailings appropriately as they leave the plant, and that will use problems later. So in terms of sampling, I can see this space actually sort of evolving very quickly. And what will be required of feasibility studies of all kinds will require more characterization measurements. And as for how to do it, what I saw in the geometallurgy research 10 years ago when mineral processing came to geology. Now, people have been talking about geometallurgy for 50 years and it was seen as common sense. But at the time, the actual technical processes had to evolve. Both the geology side and the comminution side, which I was actually part of, had to actually change how they saw the deposit and also how they actually measured their, when they took a sample, what did they take a sample for, and how do they use the information? All of it had to change. And I think that is what's required here. So when we're looking at a tailings dam, what are we taking samples for, and how do we use the information? And what we're doing now at the moment is better than has ever been done before, but it's nowhere near good enough.
So, yeah, Ian, in the end of your talk, or in the middle, you raised like all these different factors that go into your resource, or into the project prospect, basically. And this, I'm wondering, do you think the biggest challenge lies in geometallurgy, Simon, or in Ian, or is that the biggest challenge, or is it something like ESG or sampling?
Changing the culture in the mining industry on how they see this whole enterprise.
Okay.
Yeah.
Thanks, Simon. And from your perspective in the industry, Ian, what's the biggest challenge?
Yeah, I think the industry views tailings, as I said earlier, as these nice, simple, homogeneous things, but they're extremely complex. And on top of that, it's the most complicated part of the ore body. It's the bit that didn't want to come out the first time. It's very easy to understate just how difficult tailings are to treat.
Yeah. Agreed.
Great. Yeah. Well, it sounds like the geometallurgy is going to be a critical point there, as well as the perception of that and how complicated it is. So we've got a couple more questions in the chat there. Bjorn, if you'd like to unmute yourself, you could ask your questions.
Sure, there were just two simple questions. The first one was to Ian to find out whether he'd considered BIOX technologies for that refractory gold, and if not, why not? Probably economic, I guess. And then just to Simon to ask about the time it took for the scanning XRF to produce those 20 micron maps. It's just a small question out of interest.
Okay, Ian, let's go for you first.
Yeah, sure, Bjorn. I guess we've developed a particular leach methodology that we're very keen on, but we're very agnostic when it comes to process, and we'll use whatever process works best. So we certainly haven't discarded BIOX. It's on our list of comparative methodologies to assess wherever we're looking.
Thanks, Simon, over to you.
So each map took a couple of hours to run. Now what they would do is they'd run one element at a time, and then they'd merge them all together. And so I handed in, let's see, 5 drill core samples. Each one had 3 drill cores that were put parallel on the actual imaging screen together, and the results came back 2 or 3 days later. and all merged together. This is a tool I've not seen before, and the implications of what it suggests here is really interesting, because the next generation of XRF might have a resolution small enough to replace MLA. And we could do that at the mesoscale in a drill core that you can handle. Yeah. Watch this space.
Thanks, Simon. Yeah, I think very rich data sets you'd be generating.
Yeah. So, and what's interesting is when we generate these data sets, is we use maybe a tiny fraction of that data to hit our targets, and the rest is actually not used very effectively. So,
yeah, I can give it to the academics. We'll take it.
Loot and pillage.
Thanks, Simon. Carol, I think you had a question there.
Yeah, Simon, can I, so I would like to know, in your opinion, for the concentrate of the tailings, what would be the best application for it? Because if you reprocess the tailings for acid mine drainage, you will have a concentrate that is really enriched in sulfur. How could you use this concentrate? What purpose?
So how long's a piece of string? Every deposit's different and every tailings dam is different.
No, for the one that you're studying, I mean, for the...
So I approach these things in terms of, I'm assuming it's going to be a combination of 2 or 3 things together. There's very rarely a magic bullet. And especially when you go through the tailings dam, and you might sort of have one situation at the beginning, at one end of the tailings dam or at the surface, and another situation when you get down to the bottom. Because when the mine first opens, they're still learning how to extract the ore, and they're also under very serious pressure to pay off their capex. And so they'll make decisions based on high grading the deposit in the beginning, and then as the mine site comes to an end, things have all calmed down, and we have a more stable approach to everything, well, in theory. And so what I think in terms of, if we can actually remove as much mass as possible not using chemicals. Like, gravity is quite cheap and it's quite simple. Can we do that? And so we would like a situation, for example, if we need to do leaching, wouldn't it be nice if we didn't have to leach the entire deposit? Right? And so they'll often use like magnetic separation to clean the flotation concentrate. Right? Or can we now use that to process the tails? And there are logistical problems of like, how fast can you actually process these things? Remember, once the tailings are generated, they just want to get it out of the tailing pond. They don't want to slow the whole plant down to have the optimal extraction. So it's kind of like, can gravity and magnetic remove as much mass as possible in a way where we don't use chemicals at all, right? And then this says, all right, then what's left? Then we've got leaching of several kinds, and there's also the possibility of extracting metals with electrodes in slurry, directly. It's like a form of leaching that's now sort of coming out. So it's like a process. I'll start with gravity, and then I'll go to magnetic, because magnetic requires capex, and it's harder to deploy at when you're talking about a lot of samples. And then I'll go leaching. But then everything's got to be optimized together, because if you do leaching, then you've got a chemical plant that you've got to handle and make sure it's actually operating correctly. And it's also mindful to keep our target at the end. One target is how much material do we have to extract out to knock out the whole acid mine drainage problem, right? And the second one was, there's actually metals in here that are actually useful and economic. And can we extract those? And we've got to balance those 2 questions as well. And so everything's got to be balanced in a systems term, but you start with one process with the assumption there's no magic bullet. You've got to look at several processes.
Yeah, it seems definitely key to this whole problem.
Students with tweezers. Yeah, that's the most effective separation method we've got so far. You hang the student by the ankles over the conveyor belt with tweezers.
I'm glad that I wasn't that student. Perhaps so we've talked a bit about the problems of and the challenges of extraction from these mine tailings. Perhaps now, Ian, I go to you. You talked about a critical part of this process, of course, being ESG. And in my mind, like looking at, you know, traditional deposits, that's critical, of course. But here, looking at mine tailings, I just wonder if you could comment on how that differs, how the ESG and social license to operate difference between traditional open pit or underground mine deposits and tailings deposits.
Yeah, I guess the two case examples that I put up are a little bit different, and it really the ease with which you can set up an operation and get a social license depends on I guess community acceptance of what you're doing. Hellier, for example, is still an operating mine, and we really, other than ticking a few boxes for altering the methodology and techniques used on site, that will be pretty straightforward. But you go to a place like Buckens, where the mine has been closed for now 40 odd years, there may well be some resistance to setting up operations. I think certainly at the jurisdiction level, what we're proposing to do is improve the environment and take metals out of tailings, particularly when they're in a lake, for example. I think that there'll be a lot of acceptance of what we're trying to do, but I imagine there's probably other places around the world where they're glad that the mining has stopped and really don't want it to kick off again. Nice rural Freiburg, where Rosie's done her studies, springs to mind. If you look at Freiburg on Google Earth, it's nice and rural, and yeah, I guess it really boils down to what the local community thinks.
Mm-hmm. Yeah, thanks, Ian. Simon, what about you? You know, being in Europe yourself at the moment, like what do you think the perception is in terms of ESG around tailings?
They see everything in isolation. Like they have a mentality where mining is seen as dirty and we're not to do it at all. And so there's a resistance here in Finland. In Finland, it's actually possible to do mining in ways that's not possible in the rest of Europe, but the community is traditionally against it. What I think will happen is the work I'm actually sort of doing on another front is showing that we don't have the minerals in the ground to make all the solar panels and wind turbines and batteries that we need to phase out fossil fuels, and we need to do it reasonably quickly. And so at the same time, our reliance on China and Chinese systems outside of Europe is going to become more problematic. And so the very people who are against mining at the moment of all kinds, or any industrial issues at the moment, will all of a sudden not be able to buy the latest iPhone. And then those same people will demand their local politicians, I don't care how you do it, but you will fix it. See, when I first arrived in Europe, it was apparent that the mentality in Brussels, in particular, in the European Commission meetings, is they don't do mining here. They don't extract raw materials. They buy metal off the markets, or they buy finished products from China. So the realities and practicalities of extracting raw materials is not part of the consciousness here. And they're starting to learn the hard way what that means. We don't manufacture much either.
Do you think that, I mean, it sounds like tailings are quite a complex problem that we have ahead of us. Do you think it's still worth it? We're still doing the right thing by investing?
No, absolutely, because there's a movement building quite strongly that our waste products actually may well contain valuable metals and materials. And that's actually like the circular economy actions in Europe quite strongly. So we will preferentially go after industrial waste products instead of fresh mining of fresh deposits. Now that is what they're saying. What they're doing is something else at the moment. But I do believe there'll be a situation where metals and minerals in general will become much more valuable than what they are and much harder to get hold of, at which point every industrial waste site on the planet is now going to be seen as a possible mine. And so, yes, you're on the right track at the moment. The industry around you probably doesn't understand why that is yet.
And also, it sounds like there's a lot of challenges ahead, but I'm very glad that we have both of you and also Rosie working on this, and teams around the world like EnviroGold as well. So we're just coming on 11, and it's been a really interesting discussion. Thank you both for contributing on different aspects of the discussion and also different aspects in your talks. And Carol, do you have any final questions? Otherwise, I think we'll wrap up here.
No, I think it's okay. No more questions.
Okay, so thank you very much for everyone who's hung out and listened into the discussion and for your questions. And thanks again to both Ian and to Simon for joining us, also to Rosie.